So during this talk that I'm giving, sort of the idea is that I'm going to spend 1/3 of the time explaining or talking about Kubernetes, a cluster management system, about 1/3 of the time about CloudABI, a project that I've been working on over the last couple of years, and then the last third of the talk is going to be about how I've managed to let the two sort of integrate with each other. So first of all, Kubernetes. I think most of you have already heard of Kubernetes over the last couple of years. It's a cluster management system that's becoming increasingly popular over the last couple of years. Project, I think, was open sourced in late 2015, early 2016. And it's basically Google's open source version of their Borg cluster management system. Unlike Borg, which was written in C++, Kubernetes is mostly written in Go, almost exclusively written in Go. And it can be run both on a variety of cloud providers. For example, you can use it on Google's compute engine. They even provide a managed solution called Google Kubernetes Engine, Google Container Engine, GKE. Nowadays, even Amazon offers an in-cloud version that's still in beta, but even if you don't feel like using that, you can already spin it up yourself on EC2 instances running on their cloud infrastructure. But you can also perfectly run it on-premise, even though you will need to spend quite a lot of effort getting all the networking and the storage right. It's a project that was first released by Google, as I said before, but nowadays it's sort of donated to a foundation called the Cloud Native Computing Foundation, which is sort of a strongly related to the Linux Foundation. I think it's sort of like a daughter company or daughter foundation of the Linux Foundation. There's also a lot of other interesting projects that are managed by that same foundation. For example, the Prometheus monitoring system that we also heard about yesterday. Then there's also a very commonly used RPC framework called gRPC. Like almost all of the projects released by the Cloud Native Computing Foundation, Kubernetes is Apache 2 licensed. So to get a good idea of how Kubernetes works, it's always good to sort of know something about the terminology that's used by the Kubernetes project. So whenever you're reading through their documentation, you often see a couple of keywords pop up. And one of those is a node. And a node in a Kubernetes cluster represents a Linux-based server. Well, nowadays, there's a sort of a bit more freedom what kind of operating system you can use. Microsoft is even working on porting Kubernetes to Windows. So you can have a hybrid cluster where some of the nodes in the cluster are based on Linux and others are based on Windows. On these nodes, you can schedule containers. And a container, well, it's the same thing as a standard Docker container. It's a group of Unix processes that share the same namespace. With that I mean, whenever you run PS inside of a container, you only see the processes running in the same container. And every process in the container has the same view of the file system. In the case of Kubernetes, there's sort of an extra abstraction that they've added on top of this, and this is called pods. A pod is a group of containers that always needs to be scheduled on the same system. There are some cases in which you don't want to give Kubernetes the freedom to schedule containers across any kind of system you want, because certain containers might have a strong dependence on each other. For example, they might communicate through UNIX sockets, or they require memory mappings that need to be shared, or files in a certain volume that don't need any permanent storage. A common design pattern that you sort of see pop up over the last year is a so-called sidecar. Sidecars are sort of supporting containers. So, for example, if you're running a web service in a container, you might run a sidecar that writes all of the logs to a permanent log structure, a logging system. And on top of pods, there's an even higher level of abstraction, and that's called a deployment. And a deployment is a group of identical pods that should be fired up on the cluster. So if you're running a web service, it might be interesting to spawn up 5 or so of the same container, so you can spread the load, or you can also tolerate some nodes some pods being down. And Kubernetes provides some sort of built-in workflows on top of these deployments. So you can do rolling updates whenever you say, now switch all of these pods to this new version of a Docker container. It doesn't simply shut down all of the containers and start up new ones. No, instead of that, it slowly terminates them one by one, replacing them by a new pod that uses a newer version of the software. And because of health checks that you can configure, it's even the case that the update of a container won't make any progress if the new container doesn't come up healthy. And all of these objects, they can be configured through JSON or YAML files. So this is sort of a simple example of what a Kubernetes cluster could look like. You could have 3 nodes, nodes SV 1, 2, 3, and in this case they're running a total of 4 different pods. All 3 of them are running a pod for a web service, www- some randomly generated name, and inside of those pods you're running an Nginx container. All of these pods, they serve some kind of web application that needs to store some state. So you might also be running a MySQL or a database pod that's running a MySQL process. And it might also be the case that you're running some kind of strange database service that requires some periodic garbage collection or compaction. And that could be a separate container running in the same pod. All of these nodes in the cluster, they're running a process called the kubelet. And the kubelet is a process that does nothing more than fetching the desired state from the API server, like these are the containers that I should be running on my node, and then trying to apply that to the local system. So it will kill pods that are not supposed to run, and it will spawn up new ones if they are missing. The API server, this is sort of a like somewhat simplified drawing of what an API server, like how you could use it, but in practice you see that people also use multiple API servers with some kind of with an etcd database behind it that's also spread out across multiple systems. So when using a setup like this, you can also tolerate the API or one of the API server systems being down. The API server is doesn't implement any of the control loops of the cluster. So that means if you would only spawn an API server, the cluster wouldn't perform any actions based on the commands you run. And the reason for that is it uses separate processes like the kube scheduler and the kube controller manager to implement all of the workflows that are needed to keep the cluster operational. So for example, when a new node registers against the cluster, it also needs to have an IP address range, something I'll discuss next. And that IP range is being handed out by the kube controller manager. Also the same thing, when a node dies and pods running on that node need to be rescheduled onto another system, then the kube scheduler kicks in and reschedules those pods. So this is an example of what a pod declaration looks like in YAML. So it's pretty straightforward. At the top there's always a kind and metadata block explaining what type of thing you're trying to declare here. If I would have said kind deployment, I could have created a deployment. The metadata, you can specify a name. In addition to that, you can also specify a so-called namespace, which is quite useful if you have multiple parties making use of a single cluster. And then underneath, there's a specification of what this thing should look like. Namely, we want to spawn up one container using the Nginx image, and it should listen on port 80. And then at the very bottom, you see how you can create this. So this will spin up a pod, and then using kubectl delete pod, you can terminate it again. So networking in Kubernetes, that's something you could write an entire book about, but I'll try to cover it in a small number of slides. First of all, you have inter-pod traffic, so communication between different pods running on a cluster. There's one type of abstraction that Kubernetes has added, and that's called a service, and a service is nothing more than sort of a pattern matching on pods specifying these pods all together, they form one service collectively. They all, when you send traffic to them, they should all behave in a similar way. And what it does, it attaches a single RFC 1918 address to a set of pods. So what I failed to mention 2 slides ago was that every pod that you spawn up gets its own IPv4 address. But by using a service, you get one IPv4 address extra. And if you send traffic to that one, you automatically get load balanced across all of the pods belonging to that service. Then there's also 2 supporting processes that you typically run in a cluster. One of them is a kube proxy, which you run on every node, and that one automatically generates IP tables rules to do the load balancing for you. So this makes sure that when you connect to the IP address of a service, that you actually end up on one of the pods. It's a whole pile of IP tables rules that are generated on every node in the cluster. And then there's kubedns, which is a simple DNS server where you can simply do a DNS resolution for name of the service dot name of the namespace dot svc. So for example, my web service dot default dot svc, and that resolves to the IP address corresponding to that service. When dealing with external traffic, there's multiple ways you can set it up, but assuming that you're dealing with HTTP traffic, what you typically do is you make use of an ingress controller. And an ingress controller is nothing more than a single reverse proxy that examines the host name that was used for the request in the path, and based on that routes it to one of the services running in the cluster. So this is typically very useful on cloud providers where you have to pay a lot of money for every single IPv4 address you have. By using an ingress controller, in theory, you only need a single IPv4 address and you can serve all of the web applications running on the cluster. So Kubernetes is pretty awesome, but you know, for the purpose of this talk, I also want to share some of the weaknesses I think it has. So Kubernetes eats a lot of IPv4 addresses. It's insane. Every system on the cluster needs its own /24 IP range because every pod that's scheduled also has its own IP address. So using this approach, you can schedule up to 256 pods on every single system. So on a moderately sized cluster, you know, think of some kind of computing cluster, you know, one that they probably have at a university. It means if you have 256 nodes, you're already consuming a single /16 only for handing out IP addresses. And also the tracing and debugging of service traffic can be fairly annoying at times because of all the IP tables rules that are generated. On the client side, it's hard to determine, or it's hard to check if you get an error, which of the backends return this error. So if you have a huge number of microservices all connected to each other, you need to add a whole pile of extra HTTP response headers and request headers to get some basic tracing working, which is kind of nasty. In the past, what I've also seen is that if load is pretty high, then kubeproxy sort of fails to catch up with changes to the cluster. So I once even experienced that Kubernetes was sending traffic to the wrong jobs because the IP addresses that the pods were using were being recycled too quickly, which is pretty insane if you ask me. So in my opinion, it's sort of not secure enough to host arbitrary containers, you know, one cluster per customer and not one cluster serving multiple customers. And also, in the end, it's still running POSIXly based applications. And you know, containers, they don't completely take the complexity away of that. So in the end, the only thing you want to do is, you know, serve some HTTP. But in the end, you're still messing around with why does my system 5 semaphore not work on my cluster. So in the end, sysadmins now need even more skills. They both need to have an understanding of POSIX and Kubernetes. And also, the system call interface of Linux is insanely large, so you still end up with the problem that, that a large kernel attack surface remains. So again, the choice of making use of POSIX, which is completely understandable, still implies that it's, in my opinion, not safe enough to run arbitrary containers. And the final weakness is that it also somewhat promotes a cargo cult programming mentality. So what you often want to do is you want to run multiple setups of the same service. So for example, a production setup, a development setup, and a QA setup. If you're using a lot of sort of off-the-shelf open source software, that means that you need to change configuration files of those pieces of software to point to the right systems on which they depend. So for example, for web servers, they all need their own separate SSL certificates with separate host names in them, for example. They might make use of a database system, so you need to provide the proper database name, and if you fail to do that, you might actually be writing to the production database from within the staging environment. So what you often see is that people use things like either environment variables or, well, config maps in Kubernetes terminology to pass those things in. But you often see that they then need to be placed inside of the configuration files of the services running on the cluster. So you see that the entry point of a container consists of getting stuff from the environment, regexing some configuration files, and then starting up the system. And that sort of happens a lot, and you see that it blows up the complexity of a container significantly. You know, especially if you want to have properly encrypted connections between pods in a cluster, then you also need to sort of create your own SSL keys and make sure that all of the pods get them individually, and that's sort of quite a painstaking effort. On the other hand, Kubernetes also has quite a lot of strengths, in my opinion, and I think, in my opinion, it's also the future of cluster computing. You know, in 5 years from now, I wouldn't be amazed if like more than half of all computing clusters in the world will be based on Kubernetes. It all works really reliably. I've had I was able to maintain a couple of Kubernetes clusters over the last couple of years, and it is quite robust, especially if you set up redundant API servers. It's pretty hard to kill a Kubernetes cluster. It is a tool that can be used to sort of easily get 4 nines of reliability. Also, the rolling updates that are automatically built in by using deployments allow you to have 0 downtime when doing rolling releases of software, and yeah, that's really good. I've also seen a lot of worked a lot with people that had never used Kubernetes before and suddenly had to use the kubectl command line tool. It's something you get used to really quickly. It has a pretty regular syntax. It's always kubectl, get, create, delete, pod, service, whatever. So kubectl delete pod, kubectl create service. And once you're sort of used to that like the style of the commands, it's also really easy to sort of extend your knowledge by setting up even more complex constructs. Because in addition to deployments, you also have a lot of different types of primitives for constructing jobs, like daemon sets and stateful sets. And the project also has a lot of funding. Google is investing a lot of money in it. Red Hat is investing a lot of money in it. The Linux Foundation itself. And you see that there's a really healthy ecosystem of companies and individuals contributing to the project. So now that I've talked about Kubernetes, I'm now going to speak about a project that I've been working on over the last couple of years called CloudABI. And it's always hard to sort of capture what CloudABI is in one slide. So, well, still, let's try. You can think of it as a sort of heavily stripped down POSIX-like runtime environment. So if you look at the complete POSIX specification, there is on one hand a lot of ancient garbage in it, and on the other hand there's also a lot of stuff in it that might be insecure to use, and all of that stuff has been removed. So basically I've ended up with a sort of UNIX-like system that is 50 or so system calls big. I think it's even less, 45. And what's interesting about the combination of system calls that I've picked is that because of the selection I've made, it's become a capability-based system. And with that I mean there is no longer any support in it for example, permissions on files, but the security model that the system uses, if you manage to get a file descriptor pointing to some kind of resource, it could be a socket or a file on disk, you're allowed to use it, but only if you're allowed to get one of those file descriptors. And using this model, you can design programs that are effectively black boxes. So the only way you can get them to work is by sort of plugging them in on startup, hooking them up to the things they depend on, and then sort of pressing the play button. So, for example, a web server, if you wanted to design a web server on CloudABI, by default it wouldn't be able to access anything, but by providing it a file descriptor to a directory containing files that need to be served over the web, and by providing it a network socket on startup, it is able to receive incoming requests and load files from disk. So the goal of CloudABI is to make it a lot easier to design programs that are strongly sandboxed. If you sort of look at the security frameworks that you have on Linux, for example, seccomp BPF, they're always sort of stapled on. You first design an application and then later on you try to make it more secure by adding a security policy, but it's really hard to determine whether the security policy you've written completely specifies the behavior that the program can have. Well, that's not the case with CloudABI, because it's sort of like you could even think of it like an object-oriented Unix in a certain way. You get the file descriptors on startup that correspond to the resources that the program can access, and those file descriptors get passed around through the program. So it becomes really easy to distill what kind of resources the program depends on. CloudABI also is intended to sort of stimulate easier testing of applications, because all of the resources are passed in on startup. You can also stub them out and replace them by mocks. So, for example, a web server, instead of passing in a directory containing the actual files to the production site, you can pass in a directory containing some simple mockups that you can then fetch through the TCP socket. And the same thing with networking. You can easily replace a networking socket by a fake socket that sends over a series of pre-programmed requests and checks the responses. And in my opinion, CloudABI programs are also a bit easier to deploy. Normally a program on Unix, you have no idea what it's about to be using. Could open a file underneath /etc without you knowing it. You can only discover this by doing tracing. Well, that's not the case with CloudABI. Because those resources are injected explicitly on startup, it's sort of impossible to omit certain things that need to be added. So here's an example of what a simple C++ web server would look like in CloudABI. This code is sort of a bit outdated. There are some tiny tweaks that need to be made nowadays, but it still serves as a good example of what the intent of CloudABI was originally. And this code consists of two separate pieces. So first of all, the code that's sort of in bold right now is the initialization code, where the program starts up, and from the environment, it's able to extract the file descriptors that it should be using. So a normal Unix program makes use of environment variables and command line variables. On CloudABI, this has sort of been replaced by a tree that can not only contain strings, like command line arguments, it can also contain file descriptors. And in this example, you see that we're sort of looping over this data structure that's being passed in. And whenever we see a key called HTTP socket, we know that the value associated with it is a file descriptor which we extract. And the same thing holds for the root directory, which we also then extract and store. And then what we can do here at the bottom of this application is that we simply use that HTTP socket to accept incoming requests and use the root directory to look up files on disk. So a lot of the initialization code that's normally part of a program to parse configuration files and based on directives in the configuration files acquire the resources, all of that stuff is sort of being removed and replaced by a mechanism where we can inject resources into a program. So then the question becomes, how do you start a program like this? Because normally on the, if you're using bash or some kind of shell, it's not very easy to pass in sockets to applications. Well, to solve that, I've made a launcher utility called CloudABI-run. And what you can do with that is you can write a YAML file where you can design this tree. And in addition to using scalar values, strings, etc., you can use special tags like !file and !socket to add file descriptors to that part of the tree. So in the end, the only thing that gets passed to the application is a simple map containing of HTTP socket referring to a file descriptor, root directory pointing to a file descriptor, and log file pointing to a file descriptor. So an interesting aspect of CloudABI is when I was designing this was because CloudABI is so compact, it was also pretty easy to make a formal description of what CloudABI is. So here on this page, which I can open up, here I had to set it to a pretty low resolution, unfortunately, to make the projector work. You can see that, oh, what's going on with my laptop now? Hello? Looks like I made Chrome crash. Chromium browser. Okay, let's try that again. No, I don't want to restore. Oh, now it terminated immediately. Oh, this is truly the demo effect, right? Okay, so fortunately, what I do have and what I can show is that here, yeah, I have actually the repository checked out. Good thing I did that before the talk. And this is sort of what the file looks like. It's a huge like a huge file of 1900 lines, explaining what all of the system calls look like, and sort of this abstract language explaining what the inputs and the outputs are. So in this case, the system call for creating a thread is called thread create, and as an input it takes a pointer to some attributes, and then as an output it returns the thread ID of the new thread. And what we do with this file is we do a lot of interesting things. One thing that I can't show you, unfortunately, because my browser is failing, is we're automatically using this to create documentation. But we're also creating bindings for multiple languages. So we've created a container for Rust, which allows you to invoke CloudABI system calls directly from Rust code. And we're also generating source files that are used by CloudABI C library. And even more interesting, we're creating source files that can be used by implementers of operating systems to add support for CloudABI. So CloudABI is supported by FreeBSD, for example, and to implement that kernel module, cloudabi.ko, we're using header files that are generated by from the definition that's stored in this repository. And by having this sort of separate definition that can be reused quite easily, CloudABI itself is also reusable. So we have one binary format that can be used on multiple operating systems. You can compile an application on Linux and simply run it on a FreeBSD system, or you can compile it on a Mac and run it on a Linux system. It's absolutely no problem. So for FreeBSD, we're providing native support as of FreeBSD 11. For other operating systems, we don't provide any native support yet. For macOS, it's pretty hard because that would require us to change the Mac kernel, which is possible, but it's, well, asking our users to install a customly compiled kernel on their Mac, that's out of the question. For Linux, there is also a port, some modifications to the Linux kernel that allow you to run it. But unfortunately, it also depends on another patch set for Linux that hasn't been upstreamed yet, Capsicum Linux patch set. So for the time being, we ask people to make use of the CloudABI or the emulator that's integrated into CloudABI Run. So if you pass in CloudABI Run -E, you can run such programs on macOS and Linux as well. The only downside of this approach is that it's not actually sandboxed by the operating system. It's running as an ordinary Linux or macOS process in the same address space, so it's not providing any added security. Yes, so now I'm going to talk about how I've been able to integrate support for running CloudABI executables on Kubernetes. So older versions of Kubernetes, the first ones that I actually started using, I think I started using Kubernetes at around 1.2, sort of strongly depended on the Docker daemon. So Kubernetes was designed to run Docker containers and only Docker containers. What would happen is that the kubelet binary running on every node on the cluster was responsible for setting up all of the networking, was responsible for creating the so-called pods. And after it had created that, it would send an RPC to Docker saying, now please run this container inside of this pod. And this was a really strong coupling. Some people in the community also didn't like this because in addition to Docker, there's also some other container-like systems like Rocket, and those were sort of excluded from being used in Kubernetes. So when they launched Kubernetes 1.5, they added something called the CRI, the Container Runtime Interface. And by making use of the CRI, the kubelet no longer directly talks to the Docker daemon, but it sends RPCs over to a separate service called the runtime service. And the runtime service is responsible for creating the pods and the containers. Meaning that you could now finally substitute the Docker daemon for example, the OCI container daemon or Rocket. They also had a separate service called the image service, and that one's responsible for downloading images. So before firing up a container, the kubelet always sends an RPC to the image service saying, could you please download Nginx for me if it's not downloaded yet? So what I decided to do was to make use of this interface to add support for CloudABI. So I've written my own CRI, my own container runtime interface called SCUBA, Secure Kubernetes. And it consists of two separate processes. So an image service that simply downloads ELF files and stores them in a directory on disk. And then I've got a runtime service which, based on calls coming from the kubelet, spawns up sub-processes. And with the YAML file that I've shown in some of my earlier slides, where you could see that I made use of exclamation mark file and exclamation mark socket, you can't use those in Kubernetes, but I decided to add some alternatives to that are sort of better tailored to Kubernetes. So if you want to write to the Kubernetes log file, normally every container running on Kubernetes has its own sort of log output. You can use the tag exclamation mark Kubernetes/container log, and there are special tags Kubernetes/server and client for making network connections. And with Kubernetes/mount, you can access certain mounts. So if you're running on for example, on Amazon AWS, normally you can make so-called persistent volume claims that allow you to access an elastic block store device. Well, with the Kubernetes/mount tag, you can access such block devices. So So this is what it looks like when using Kubernetes in combination with Scuba. So the kubelet sends RPCs over to the image service and the runtime service, and the runtime service is responsible for launching the sub-processes. So when I was implementing this, I managed to get some simple processes working that were able to write data into the container log. You know, your typical hello world. That was the first thing I managed to run on my patched up version of Kubernetes. But I quite quickly discovered that there was sort of still one missing piece to the puzzle, and that was that networking didn't work at all. So as I mentioned before, CloudABI programs can't simply create network connections out of thin air. They need to be injected into a program for them to work. And Kubernetes is sort of built around the model that programs can make their own network connections. If you look at a definition of a pod or a deployment, nowhere is it specified what kind of backend services it uses. That's all up to the program. The program is responsible for making those TCP connections. So I decided to design something called Flower, and at the same time I'm also trying to solve some other problems that networking on Kubernetes has. So for example, at least by default, there are no proper tools available in Kubernetes for having proper tracing and debugging. You're making a direct TCP connection to some other process on the cluster, and there's no easy way to capture that. So because of the security model of Linux, it's not simply possible to attach to a container and run TCP dump in there. You know, it's all a single network stack on a single Linux kernel that deals with the traffic. So debugging is pretty hard, tracing is pretty hard, and also with security. By default, there's no security policy in place on a Kubernetes cluster. So Kubernetes hands out these IP addresses, all of these /24 IP ranges that they have on those servers. Every pod gets its own IP address, but there is no security, no firewalling being applied by default, which is pretty poor. And in addition to that, because you're dealing with IP addresses and not with any decent names, there's also no support for getting proper metadata passing. So whenever you receive a connection from some other pod, the only thing you know is its IP address, but you don't know the name of the pod. The only way you can figure out the name of the pod is by sending an explicit request to the API server to request the pod's name. So I decided to design something called Flower, and Flower is a simple daemon that sort of tries to move the networking part out of the kernel into user space. And with that I mean there is a process called the switchboard, and the switchboard can be used to sort of register services, and other clients in the cluster can send RPCs to the switchboard to ask for connections. And Flower, whenever it makes a successful match between the client and the server, it creates a UNIX socket pair and hands out both those socket pair halves to those processes. So I can show on my laptop what it looks like. Flower can be used in combination with CloudABI, but I'll first start off with sort of demoing what it looks like if you're using it outside of CloudABI. So it's nothing more than what I'm doing with this command is I'm firing up a so-called switchboard process, and the switchboard is going to sort of run on /tmp/flower. What I can now do is I can run another program called flower cat to listen on the switchboard. So I can say on tmp flower I want to listen, and in this case I want to give this program a certain identifier, namely program chat. Now in another terminal I can run another copy of flower cat. So you see that I'm running exactly the same command except that I'm not passing in the -l flag. And now you see that it successfully made a connection between the two. So now I can chat back and forth. Oh, hi, hello, goodbye. Here, and then it's sort of shut down. But there's a lot of sort of utilities that come with this to make more complex setups, because this is of course not really interesting. So one of the things I could be doing is I have a simple demo here, cat webserver.yaml. Here, this is a simple web server that I'm now going to spawn up. So this is a YAML file, the definition of a CloudABI program, where I say we need to write log file output to standard out. This is the fixed response that my web server needs to return. And this is the Flower switchboard it needs to use. It needs to register prog is web server on TMP Flower. So by running this, and let me close this terminal, I can now, or wait, what I can do is I can run another program, Flower ingress accept, and what this will do is it will listen on port 80 on my system, and whenever it receives an incoming connection, it will send it to the switchboard running at TMP Flower to the program having these labels. And now let's hope that my browser doesn't lock up. Voila. So what happened now was that in the browser I made a connection to this Flower ingress accept, which then pushed the incoming TCP connection over to the switchboard, which then looked through its list of services and handed the TCP connection over to the process on the other side. And this is a pretty flexible piece of software that's already quite usable outside of CloudABI, because what you can do with this, for example, is make a Flower ingress accept that can do SSL termination for you, and then you don't need to add any SSL logic to the web server. Or you can run multiple copies if you want to let a program listen on multiple TCP ports. That's all sort of done by using smaller utilities for setting this up this way. So I guess I unfortunately closed my slides, but that's not a problem. I can open them up again. Presentation. So yeah, this is what I've showed in the terminal. So what is interesting about how Flower works is how the matching strategy of the labels worked. So far in the demo that I gave, all of the label matching was done exactly. You saw that I made a chat client sort of, or a chat server that was running on program chat, and then I made a client that was connecting to program chat as well. But the label matching that's being done by Flower is actually a bit more complex than that. So a client and a server are matched up with each other when there are no labels that contradict with each other. And by using this approach, clients and servers can attach extra labels to any of the connections. So a client could, for example, have a label saying client address is some kind of source address, IPv4 address even. And a server could also add some extra labels saying Apache version is 12345. And by adding those labels, you can have sort of a better insight in both of the parties. So the client will get more information about the server after a connection has been set up, but the server will also get more details about the client. And inside of Kubernetes, this could also be used to attach additional labels to connections that are coming in on a cluster. So whenever a connection is going through some kind of load balancer, a load balancer could also attach a label on this saying load balancer address is some kind of, or load balancer hostname or process ID of a process running on the cluster. Just like CloudABI itself is capability-based, Flower is capability-based as well. So processes, whenever they have a handle to the switchboard, they can sort of duplicate it, but they can also constrain it further. So they can add labels that need to be tied to any connection made by that client or server from that moment on. And this is something that I'm using inside of inside of Scuba. Namely, whenever Scuba launches a sub-process, it gives a handle from the Flower switchboard to a process that allows it to create a network service that already has some labels stapled on that can't be erased. So, for example, the name of the pod, the name of the container, those are labels that are immutable and should not be changed by processes running on the cluster, because then they could impersonate other processes. Okay, so this is the sort of resulting setup where I have, similar to the previous image, except that now there's a Flower switchboard also running on the cluster. And the Scuba runtime service is handing out additional connections to the Flower switchboard to every container it starts. So, wrapping up. What I've discussed in this talk is there's a cluster management system called Kubernetes, which is already pretty awesome on its own. But I'm working on a piece of technology that will make it possible to run strongly sandboxed applications on top of it, called CloudABI. Scuba is the name of the service that the container runtime daemon that allows you to run them on Kubernetes, and Flower is the networking mesh that I'm developing to make communication between such sandbox processes possible. To finish with my slides, here's a list of interesting links. I'll make sure that the organization of the conference also gets a copy of these slides, but the top link is the official site of CloudABI, and underneath are a whole bunch of GitHub repositories containing the code. All of these have been discussed, except the bottom two ones. They sort of reserve an honorary mention. So ARPC is an RPC library that's being used by systems like Flower and Scuba, which allows for transparent file descriptor passing between processes. And CloudABI ports is a whole collection of pre-compiled packages of software that's already been ported over to CloudABI. I'm already a couple of minutes over time, right? Yeah, so.
Still going, so feel free to go until you've got your applause.
Yeah, really? Okay. Yeah, so I also had a really tiny demo prepared. I had a more complete demo a couple of weeks ago, but then I made the newbie mistake of overriding all of the hard disk contents on my laptop when I wanted to make a USB stick for installing another computer. So here I've got a Debian virtual machine. I'll increase the font size a bit. And this one is running a Kubernetes API server. So this is the master node of a Kubernetes cluster. If I now ask it which nodes are attached to this cluster, it will respond saying that there's a FreeBSD node attached to this cluster. So this will be the one running the pods. If I now run a kubectl describe node, and then copy paste this, you can see that this is sort of a special node because the container runtime it's using is Scuba. So it's no longer using Docker, this one is using Scuba. You can also see that I built this from Git because the version number of Kubernetes is completely messed up. What I can do now is, here in this directory, I have a simple service that I can start up here. And this is a Kubernetes deployment specification, so YAML file. And what you can see over here is that here, if I go down to the, this is where you would normally specify the Nginx container that you want to start up. But what I'm doing now is I've placed a YAML definition of the configuration of the program in there, just like with the Flower demo that I gave previously. And now I'm saying start up this specific executable, which is the checksum of the web server executable. So now if I run this kubectl create-f web server and kubectl get pods, you see that it now spawned up 3 different web server processes. Well, these are all running on the FreeBSD server. So let's FreeBSD 12 VM. If I now say Flower ls socket switchboard, you see that each of those containers running on the cluster has its own set of labels, its own identification of how it's called. So what I can do now is sudo flower ingress or flower ingress accept. Switchboard, paste this in here, and if I now open up a browser, oh wait, this is the address of the cluster, 6856. You see that whenever I load this page now, it loads it, it opens up a page of a process running on the Kubernetes cluster. So we now have a simple Kubernetes cluster running 3 web servers, and all of these web servers, the only thing they can do is pick up incoming connections, but for the rest, they are completely sealed off from the rest of the world. So this is just a simple demo of how it works. There's still a lot of development that needs to be done. If you're looking for a project to contribute to and have too much time on your hands, then please come and chat with me after the talk. Are there any questions?
No. Thank you.